By the end of the lesson, the students will be able to explain that a chemical reaction can only take place if the reacting particles collide with sufficient energy and correct orientation. Interpret Arrhenius Equation. Explain the effect of concentration and temperature of reactants on the rate of reaction. Consider the reaction A and B gives C. What must happen to the particles of A and B in order for them to react to form C? Click Next for the answer. Answer: the particles of A must collide with the particles of B. Do all collisions between particles of A and B result in a reaction? Click Next for the answer. Answer: no. Look at the energy profile of the reaction. Click the Start button. The first pair of particles, A and B, are able to react because they have acquired enough energy to form C. Note that only one pair of particles, A and B, are able to react to form C. Discuss this and click Next. This pair of particles, A and B, are able to react because they have acquired enough energy to form C. A and B must form an activated complex, AB, in order for the product to be formed. This is the minimum energy required for the formation of this complex in the transition state. What is this energy called? Click Next for the answer. Answer: this energy is called the activation energy, EA. Let us look at the energy profile for the reaction between hydrogen and iodine molecules. Click the Start button. When two molecules of hydrogen and iodine get close enough, HI bonds are formed while the HH and the II bonds weaken. The energy needed for the breaking of bonds comes from the kinetic energy of the colliding particles. The activated complex formed is the arrangement of the reactant molecules with the maximum potential energy. The HI bonds in the complex become stronger while the HH and II bonds get weaker as the reaction proceeds. The product HI is finally formed when the bond rearrangement is complete. Not all collisions between hydrogen and iodine molecules result in a chemical reaction, even though these particles collide with sufficient energy. Discuss this and click Next. The molecules must also approach each other in the right orientation. The collision theory states that for a chemical reaction to take place, the reactant particles must collide with sufficient energy and with the correct orientation. Collisions that result in a reaction are called effective collisions. The rate of reaction is proportional to the rate of effective collisions. A chemical reaction can only take place if there is an effective collision between the reacting particles. An effective collision occurs when the reactant molecules 1. Have energy greater than or equal to the activation energy EA, and 2. Approach each other with the correct orientation. Activation energy is the minimum energy needed by the reactants to form the activated complex. Click on concentration X1. Observe the number of collision counts in 10 seconds. Now, click on X2 for a higher concentration. At which concentration is the rate of reaction higher? Discuss this and click Next. The rate of reaction is higher at the higher concentration of X2. With a higher number of molecules in a given volume, the distance between the molecules is shorter. As a result, the frequency of collisions is higher. The rate of reaction is directly proportional to the number of effective collisions per unit time. The rate of reaction increases with an increase in the concentration of the reactants. Click the Decrease button to decrease the temperature and observe the movement of the molecules as well as the number of collision counts per 10 seconds. Now, click the Increase button and observe the effect of an increased temperature. What is the effect of an increase in temperature on the rate of reaction? Click Next for the answer. Answer: an increase in temperature results in an increase in the rate of reaction. The rate of reaction increases with an increase in temperature. The rate of reaction at temperature T1 is taken as R1. When the temperature is increased by 10 K, the rate of reaction is increased by 2 times. This increase in rate is higher than that expected for an increase in the effective collision frequency. To find out why, click Next. Look at the Maxwell-Boltzmann distribution curve. The shaded portion shows the number of molecules having energy equal to or greater than the activation energy EA at the temperature T1. Click Next to see the distribution curve at a higher temperature T2. What can you deduce about the total number of molecules having energy equal to or greater than the activation energy EA at the higher temperature T2? Click Next for the answer. Answer: as the temperature increases, the number of molecules having energy equal to or greater than the activation energy increases. As a result, the rate of reaction increases with an increase in temperature. The Arrhenius equation gives the relationship between the rate constant with the activation energy EA and temperature T. If we take the natural logarithm of both sides of the Arrhenius equation, we get ln K is equal to ln A minus EA over RT. What happens to the value of K when the activation energy is decreased? Click Next for the answer. Answer: the value of K increases. What happens to the value of K when the temperature is increased? Click Next for the answer. Answer: the value of K increases. The rate of reaction increases with an increase in temperature. An increase in temperature, 1, increases the frequency of collisions between the molecules. 2, increases the total number of molecules with energy equal to or greater than the activation energy, EA, for a reaction. The Arrhenius equation gives the relationship between the rate constant with the activation energy and temperature. The rate constant K increases with 1. A decrease in activation energy and 2. An increase in temperature.